Hello, geometry students. We're in section 13-2, and we have some new vocabulary. We have permutation. We have factorial. We have circular permutation. And we have combination. So moving on to our first key concept of factorial. The factorial of a positive integer written n with an exclamation point is the product of the positive integers less than or equal to n. Okay, so for example, 5 factorial means 5 times 4 times 3 times 2 times 1. So that would be 20 times 6, or 120. So 5 factorial is 120. So, here example number 1, probability and permutations of n objects. So Ellie and Mia, along with 30 other people, sign up to audition for a talent show. Contestants are called at random to perform for the judges. What's the probability that Ellie will be called to perform first and Mia will be called second? Okay, so what we're going to do first is we're going to find the number of possible outcomes in the sample space. So we have a total of 30 contestants, so we're not going to have 30 plus 2, but 32 is going to have 30. So we're going to have 30 factorial different permutations there. So now we're going to find the number of favorable outcomes as step 2. This is the number of permutations of the other contestants given that Ellie is first and Mia is second. So in this case we have 30 minus 2, or 28 factorial. Find the number of favorable outcomes, the number of permutations of the other contestants. So this could have been the same. This could have been saying that Mia was last and Ellie was second to last. It'd still be the same way. So the other 28 people, there'll be 28 factorial ways of rearranging them. And that's what that second step is saying. Okay, now we're going to calculate the probability using these two numbers. Okay, we're going to take 28 factorial, and that's our number of favorable outcomes, and we're going to divide that by 30 factorial, which is the number of possible outcomes altogether. So 28 factorial and 30 factorial are related. Okay, 30 factorial is 30 times 29 times 28 times ... all the way down to times 1. And that's 30 factorial. Well, 28 factorial is 28 times 27 all the way down to 1 times 1. So let's look at that. So the 28, the 27, the 26, the 25. From this point on, they all cancel. Only thing left over is the 30 and the 29 on the bottom. 30 times 29, we could actually multiply that out, and 30 times 29 ends up being 870. The numerator reduces down to a 1 over 870. Now if you want to write this as a decimal, I guess you could too, and that'd be like point very low, 0.0011. If you make that into a percentage, it would be 0.11%. Okay. All right, check your progress. Go ahead and pause your video. What's probably he had chosen first, second, and Brant third? Okay, and the answer is C. Now, if done correctly, this should have been 40 factorial on the bottom. And the favorable ways would be 37 factorial. And so that's going to be 1, and then 40 times 39 times 38. So 40 times 39 times 38 is 59,280. So 1 over 59,280. Okay, key concept. So those two examples kind of leads us to a key concept called permutations. The number of permutations of n distinct objects taken r at a time. So you can think of this as the number of successes. So we have then taken r at a time is we have the n factorial on top. This is the number of permutations, number of ways we can rearrange. So, and you subtract the r, taken r at a time. So the number of permutations of five objects taken 2 at a time is 5 factorial over 5 minus 2 factorial, which is 3 factorial. But 5 factorial is 5 times 4 times 3 factorial. Make sure you understand what that means. 5 factorial is 5 times 4 times 3 times 2 times 1. And since we're dividing that by 3 factorial, consider 3 times 2 times 1 to be 3 factorial. So those two are going to reduce, and that gives you 20. So you have 20 permutations of n objects taken r at a time. And we denote that NPR. Okay? That NPR can also be found in something called Pascal's triangle. So if you write down Pascal's triangle, you start with a 1, and then a 1, 1, and then we're going to put a 1 here, and then we add the two numbers right above it, 2, and then a 1. This would be a 1, a 3, and a 1. This would be a 1, 4, 6, 4, 1. Then go 1, and then go 5, 10, 10, 5, 1. Okay? So, we're going to, when we do combinations in a little bit, we'll be able to use this. Okay? Has something to do with the number right here. Okay, but we'll learn that later. Okay, move on to our 12 puppies for sale. 4 are brown, 4 are black, 3 are spotted, and 1's white. What's the probability that all the brown puppies will be sold first? Okay, well, we can figure out the number. Since the order that puppies are sold is important, this problem relates to a permutation. We're looking at the number of possible outcomes in the sample space is the number of permutations of 12 puppies taken 4 at a time. So we can write that as 12p4. And that's 12 fact divided by 12 minus 4, or 8 fact. So the 8's factorials cancel, and all we have left over is then the 12, 11, 10, 9. It's 11,800. Now the question is, what's the probability? Now that's just the number of permutations. Okay, step number 2 is to figure out the number of favorable outcomes from that 11,800. Okay, the number of favorable outcomes is the number of permutations of the 4 brown puppies in their specific positions. This is 4 factorial, or 24 favorable outcomes. So we can take 24 divided by our 11,800, and we get 1 over 495. "24 people in the hula hoop contest. 5 of them are part of the Garcia family. If everyone in the contest is equally as good, what's the probability that the Garcia family finishes in the top 5 spots?" So we're going to think about that. All right, 1 over 42,504. Okay, permutations with repetition. The number of distinguishable permutations of n objects in which one object is repeated r times, another is repeated r2 times, and so on is. So we have n factorial over the repetitive r sub 1 fact, r sub 2 fact, all the way to r sub k fact. Here's an example. Okay, a box of floor tiles contains 5 blue tiles, 2 gold tiles, and 2 green tiles. In random order, the design pattern is blue, gold, blue, green, blue, gold, blue, green, and blue. If you selected a permutation of these tiles at random, what's the probability that they would be chosen in the correct sequence? Okay, there is a total of 9 tiles. Okay, of these tiles, blue occurs 5 times, gold occurs 2 times, and green occurs 2 times. So the number of distinguishable permutations of these tiles is, like we said, as the equation, we're going to have 9 fac on top, and then 5 fac, 2 fac, and 2 fac on the bottom. So we get 756. Now that's step 1, just coming up with the number of permutations. It's because we have the repeated. Okay, so it's not just 9 factorial. It's then 9 factorial divided by the product of the repetition. So that's 756 is going to be my denominator. Okay, so then we got to go to our step 2. Our step 2 then is there's only one favorable arrangement, and that arrangement is the desired pattern. So there's only one out of the 756. All right. Here you guys try this. Go ahead and pause your video. So we have 3, 6, 7, 8. So we're at 8 factorial as my main number. Okay? 8 factorial. And we divide that by the number of repeats. So we divide that by 3 fac. We divide that also by another 3 fac. And then by 2 fac. Okay. So 8 factorial. 8, 7, 6, 5, 4, 3, 2, and 1. So 3 factorial is 3 times 2 times 1. Let's get rid of that. And this 3 factorial is 3 times 2 times 1, which is 6. Let's cancel that guy. And then 2 factorials is 2. So I can divide this 4 and get a 2. And then we can multiply 8 times 7, right, times 10. So we have 56 times 10, or 560 possible outcomes, of which we only want one of them. We want the red, red, purple, purple, orange, red, purple, orange. All right, so circular permutations, a little tricky. The number of distinguishable permutations of n objects arranged in a circle with no fixed reference point. Okay, and that's going to be n factorial over n, which just basically means n minus 1 factorial. Okay, So why that works that way, if we took 5 factorial as an example, and we divide that by 5, then that would leave me 5 times 4 times 3 times 2 times 1. If you divide that by 5, the 5's cancel, and I'll leave myself with 1 less than I started with, so 4 factorial. So that's why they call this n minus 1. So think about arranging things, right? That's what permutations are, they're arrangement. But this time we're going to go in a circle pattern. Okay? So here we go. We have our example here. If 8 students sit at a random in the circle, what's the probability that the students sit in the arrangement shown? Explain your reasoning. Okay, well, I think there's only going to be one way for that to occur, but we want to figure out, right, figure out how many distinguishable permutations there are where the students can sit. So, since there's no fixed reference point, this is a circular permutation. So there are 8 minus 1, or 7 factorial distinguishable permutations of the way students can sit. So going back to that little key concept, the number of distinguishable permutations, okay, or arrangements. We have 7 factorial ways. And we're only concerned that we have exactly this arrangement. So think about that, exactly. So we have our 7 factorial, and then we only have one of those ways that we want it to be. So it's 1 out of 5,040. Okay, here's an example. You purchase a box of 8 crayons. The crayons are packed in random order. What's the probability that the crayon on the far left is red? Explain your reasoning. Okay, since the crayons are packed in a row instead of a circle with no fixed reference point, this is a linear permutation. In that case, there are 8 positions. And one red crayon, the probability that the crayon is on the far left would be 1 out of 8. Okay, go ahead and check your progress. Okay, go ahead and pause your video. If for a birthday party there are 5 people having cake and there are 5 different colored plates, what's the probability that if chosen at random, the plates will be displayed as exactly seen? So there's only one exact arrangement that we want, right? But we know it's circular, so in this case it's exactly this one arrangement, right, divided by 5 minus 1 factorial, or 4 factorial. 4 factorial is 4, 3, 2, 1, and that represents 24. So the answer should be B. Okay. Home builders constructing different models of homes on a major cross street, 5 of which are 2-floored homes, and only one home that's 1 floor. If built at random, what's the probability that the 1-floored home will be on the first plot of land? Well, think about that. Should be nice and simple. There's only 6 possible spots. Okay, and only one way for that to be the first one. Okay, our next concept is called combination. This is the number of combinations of n distinct objects taken r at a time. This is the number of combinations of 8 objects taken 3 at a time can be found by saying 8 fac, okay, over 5 fac times 3 fac. So we're using the n minus r, right? Notice the 8 here and the 8 here. 8 minus 3 is 5. That gives me my 5 factorial. And then the 3 factorial, basically taking 3 at a time. Okay. If we were doing, let's say, do a simpler one, 4, choose 2. Okay. Written like that, or smaller 4 of the big C and then 2. Pascal's triangle actually gives us this ability. So I'm going to draw it out real quick for you again. Okay, this actually represents 4 choose 0, 4 choose 1, 4 choose 2. So the answer actually for 4 choose 2 would be 6. And we can show that here by saying that we'd have 4 factorial over 4 minus 2 factorial times 2 factorial. And that's using this right here. So 4 factorial is 24. And this right here represents 2 factorial, which is just 2. And this is also 2 factorial, which is 2. And 2 times 2 is 4, and 24 divided by 4 is 6. And lo and behold, you got the answer right here. So combinations, okay, when the order does not matter. Permutations is when the order does matter. Okay, so we have a set of alphabet magnets are placed in a bag. If 5 magnets are drawn from the bag at random, what's the probability that they will be the letters A, E, I, O, U, or A, E, I, O, and U? Okay, well, since the order in which the magnets chosen does not matter, then this is going to be a combination. Okay, so as long as we get these 5 letters is what we're saying. Okay, probably those letters will be chosen. We're not looking for the problem set, we're looking for the number of ways, right? So we're going to have 26 choose 5. All right, so 26 choose 5. 26 factorial is nice and big. So 26 choose 5 is going to be 26 factorial over 26 minus 5 factorial times 5 factorial, or 65,780. Okay? The number of possible outcomes in the sample space is the number of combinations of 26 letters taken 5 at a time. So we have 65,780 different ways of choosing 5 at a time. Now the question is, there's only one favorable outcome, right? That all 5 letters, so the actual probability of it occurring is 1 over that. 1 over 65,780. Okay, check your progress. A set of alphabet magnets are placed in a bag. If 4 magnets are drawn from the bag at random, what's the probability that they will be the letters M, A, T, and H? Okay. Again, it doesn't matter if it's A, M, T, and H, the order chosen, just M, A, T, and H. Those 4 letters are chosen. Okay, so it's going to be, you only have one possible way of doing it. Okay, there's only one. Okay, and then we have to figure out the number of ways. Okay, so think about that for a second. Go ahead and pause your video and see if you can calculate it. So, set of alphabet magnets, right? That would be 26. Okay, we're going to have 26. Choose, and we're choosing 4 at a time. So that would be 26 factorial over 22 factorial. I got that by taking 26 minus 4. Okay, and then also going to have a 4 factorial here. Okay, so we're going to figure out this. Now 26 factorial is nice and big. Okay, you can do this in a calculator, or take 26 times 25 times 24 times 23, and then 22 all the way down is just your 22 factorial. So this 22 factorial can cancel with the rest of this. So we're going to have 26, 25, 24, and 23, and divided by 4 factorial, which is 24. So these cancel also. So the number of ways is 26 times 25 times 23. Now, if you have a graphing calculator, you might be able to find the factorial button under your math key probability menu. But if not, you can just do it by hand. So 26 times 25, and then still times 23. That ends up being 14,950. So we have 1 out of the 14,950 different ways.